Hello everyone. So today we're introducing rotation. So rotation is kind of like a review of everything we've learned so far, but now instead of going in a straight line, straight back, we're going in some sort of rotational pattern. Now we have done circular motion before, but the thing that's different about the circular motion that we've talked about previously is that we have a constant velocity, and so that's sort of the basic assumption of that. Whereas when we're talking about rotational stuff, we're talking about maybe a changing velocity or a changing angular velocity. Now, everything we've learned in in linear land, so that's what we remember, everything either going forward or backwards, right? Linear land, also kind of applies into angular land. So let's go through some of these variables. So some of these may be reviewed because we've seen a little bit of these before, but displacement. Okay, so delta x, what would be the angular version of delta x? So instead of going in a straight line, I'm going in a circle. How do I count that? Yes, so that is theta, and we measured that in radians. Okay, now when we're talking about projectile motion, we might measure the angle in degrees, but when we're talking about angular stuff, going in circles, we want to use radians. Okay, and the transition, the formula to switch between these two is fairly simple. I just need to think about a circle. Okay, now if I have a circle, I know that if I do one complete revolution, one complete circle, that's 2 pi radians. Okay, so now I just need to think about how far was that in meters. Well, I have an important piece here that's missing. I need to know my radius. Okay, now how do I find the distance of this circle if I did one circle? Right, I just need to use the circumference. So the circumference of a circle equals 2 pi r. Okay, now this right here is actually the radians. Okay, so if I want to find the distance, so I change that circumference to a delta x, I just need to do the theta, the angle, times the r. Okay, so theta times r is my delta x. So next, velocity. What is the angular version of velocity? Omega, right? So it's kind of like a W, but instead of using straight lines, you're using curved lines. Okay, and then the units for this will just be radians per second. So just like we have in velocity, we have meters per second. For omega, or angular velocity, we have radians per second. Make sure you call this either omega or angular velocity. Don't say W because that's not the right term. Okay, same thing here. Since we have theta r equals delta x, we have omega r equals v. Okay, now you could obviously change this, so you could have v over r equals omega. Either one is correct. It's just a changing of variables. Next, acceleration. What is the angular version of acceleration? That is alpha, or angular acceleration. Okay, so this one is just in radians per second squared. And the transition between the two is just the same. So we have alpha r equals a. So just like we had these top three, it's basically the exact same. Okay. One thing to note for these is that the radius, we'll come back to that later, so don't worry about that yet. Yes, so next we're going to talk about some of these other ones, and we'll get more in depth to these other ones in the future. So let's talk about force. So when we talk about force, it's a push or a pull, and it's in a direction, okay? But we have an angular version of that as well. Now, the angular version of that we call torque. Okay, so it's kind of this weird letter like this. And the units for this, so the units for torque are just Newton meters. Okay, now the formula for torque is written a little bit strangely. So I have this tau is equal to, or torque is equal to r, and instead of writing a dot or something else, I actually write a cross. Now there's a reason for that, but you don't really need to know that reason right now. So it's r cross f, or just r times f. Now there's an important thing, is that these need to actually be perpendicular. If you recall work, right? The force and the distance actually need to be in the same direction. Well, for torque, they actually need to be perpendicular. Okay, once again, we'll talk more about that later. But for that reason, you can actually change it from a cross to equals RF sine theta, where we get the most torque if this angle here is 90 degrees, or pi over 2. Okay, so the angular version of force is just torque. Okay, now when we think of mass, we think of what? Well, there's two ways to define mass. One is gravity, right? So we know that anything that has mass, gets pulled on by gravity. Okay. Another way to think of mass is what? Hopefully you got it. It's how hard something is to push. So if something has more mass, it's harder to push. If something doesn't have very much mass at all, then it's very easy to push. Well, the same idea works in rotations, but we need to add some more information to this because just the mass alone doesn't give us enough information to tell how hard something is to rotate. Okay? Now, if I have something heavy like a table, okay, this is going to be hard to push, right? Because it has a high mass. So high mass means hard to push. Whereas rotation isn't only about the mass, it also is about another factor. So I want you to think about it. What would make something harder to rotate? Okay, so maybe you figured this out, maybe you haven't. But where the mass is ends up being very important. It's not just about how much mass you have, it's also about the shape and where that mass is. So for example, in this, I have more mass distributed farther away, and I have less mass right in this middle section. Okay? So what it ends up being is that there is a relationship where the location of the mass actually matters to how hard it is to rotate. Right? So rotational mass, or angular mass, what we actually call it is moment of inertia, is dependent on where the mass is. Okay? So let me put this table back. So we use I to stand for the angular mass. The actual term is the moment of inertia, and the units would be kg meters squared. Okay? And the formula is right here. Okay? And you can see that we have, I'll scroll down for a second. One second. Okay, so you can see that we have this formula here, and we have I, which is our moment of inertia, or our angular mass, is equal to mr squared. So this is only for point masses, and we'll explain a little bit more about that later. But the way this works is the radius ends up actually being more important than the mass itself. So if you have your mass distributed very far away from where you're rotating, you end up being much harder to rotate than just having more mass very close. In fact, if you have something very thin like this, where all your mass is concentrated right near the axis of rotation, you end up being very easy to rotate. Okay? So we have I. Okay? Next, we have kinetic energy. So there's actually a angular version of kinetic energy. It's very simple. It's rotational kinetic energy. So here we just do Ke rot, and then we have 1/2. Now instead of m, I need to use my angular m, which is, yes, I. And then instead of v, I need to use angular velocity, which is omega. Good. Okay? And that's still just measured in joules. Okay? And then We also have angular momentum, okay? So once again, we're taking something that is linear momentum, and we need to make it angular, okay? So angular momentum is in L, okay? So, and then our formula here, L is equal to, instead of using linear mass or regular mass, we need to use angular mass, which is I. And then instead of using linear velocity, we use angular velocity, which is omega. Okay? So, I will join you shortly on another section of the notes.